In this video, we will discuss electrical field, electrical force, and Coulomb's law. First, we're going to review the basics of charge. Subatomic particles, protons and electrons, have charge. Protons are positive, electrons are negative. This charge is quantified, and the fundamental charge of either a positive or negative charge is expressed by QE, which is equal to 1 times 10 raised to the negative 19 power coulombs. So whether the charge is positive or negative, all charges are some multiple of this fundamental charge QE. Any charge in space gives us what we call an electric field. So as you can see right here, an electric field is a region around a charged particle that maps the force that would be exerted on another charged particle. We show the field of a charge by using electric field lines. So what is an electric field line? Right here, an electric field line is an imaginary line in space that shows the electric field. So this is a charge. The charge has a field. The field is expressed or shown by electric field lines. This is the field of the charge. These are the electric field lines. It's important to note that the field lines of a positive charge are moving away from the charge. In a negative charge, the field lines are moving toward the charge. The strength and direction of the field lines depend on the charge. So a greater magnitude charge will have more dense field lines. So if you can imagine a larger value of a charge will have more field lines. And this means that there's a stronger field. So what if there are multiple charges? How do we show that? Well, like in the previous slide, we know that field lines move away from positive charges and they move toward negative charges. So here's the interaction between opposing charges, a positive and negative charge. And as we know, like charges repel, and so two positive charges, the field lines will both be moving away from each of the charges. It's important to note that these field lines will never cross. It's also important to note that these field lines, remember, are not real. They don't actually exist, but they help us understand the field of a point charge or multiple charges somewhere in space. So how do we find the strength of an electric field? Well, the magnitude of an electric field, which we'll call E, is determined by this equation. The magnitude of the electric field, E, is equal to K, which is Coulomb's constant, times Q, which is a charge, divided by R squared, R being the distance from a charge. So this equation expresses the relationship between the charge and the electric field and the distance in the electric field. As you can see, the charge is directly related to E. As charge increases, E, or the electric field, would also increase. But as you increase the distance, the electric field will decrease. And so the distance and the field strength are inversely related. Now, when you solve this equation with the given variables, you will notice that these variables, meters and coulombs, will cancel out, giving you newtons over coulomb, which is the units of the electric field. So how do we determine the electric force that will act on another charge placed in an electric field? So the electric force, which we'll call F, can be determined by the electric force equation. That is, the force is equal to the magnitude of the electric field times the point charge of interest. So this equation shows us the force that will be acting on a point charge Q in an electric field from a different force, from a different charge. And it's important to note that the force acting upon this charge is in the same direction as the electrical field, like when we were drawing the electrical field lines of a charge. So now what we're going to do is we are going to combine the electric force equation right here with the electric field equation to give us an equation that shows the force between two charges relative to the distance between them. So if we take the electric force equation and we have E here, which is, remember, the electric field. So E, we're going to plug this in to the electric force equation for E, and that will give us this equation right here, which is known as Coulombs' law. Coulombs' law states that the force between two charges is directly proportional to the product of the two charges and inversely proportional to the distance between the two charges. So you'll notice that the first part of this equation here, the K, Q1, and R squared, came directly from the electric field equation. Plugging that into the force equation, and that gives us one more charge to deal with, and that is Coulombs' law equation. So basically we're just adding another charge, we're adding Q2, and then finding the force between the two charges relative to the distance between them. So you might be thinking, hey, this looks familiar. Well, the concept is almost identical to Newton's law of gravity. So here we have Coulomb's law, which we just discussed. Looks very familiar to Newton's law of gravity. Newton's law of gravity shows the force between two objects, or two masses, m1 and m2, relative to the distance between them, over r squared. G is the gravitational constant, and Coulomb's law is basically the same thing, just dealing with much smaller particles, tiny little charges. And of course there's a different constant, the K constant, the Coulomb constant. But again, the principle is very similar. So now that we have discussed charge and the electric field and the electric force, and combine those to find the force between two charged particles, we've expressed that mathematically through Coulomb's law by this equation. Let's do a practice problem and see if we understand this principle. So two charges, 5 coulombs and 15 coulombs, are separated by 10 centimeters. What is the force between them? I invite you to pause the video, solve, and then press play when you're done. Okay, so for this problem, we will need to use Coulomb's law, and we have that equation right here with two charges and a distance and a K constant. So we know the two charges, we know the distance, and we also know the constant K. So if we plug all of those in, then we can solve for the force. And if you plug that in, you will get 6.7 times 10 raised to the 13th power newtons force between the two charges at a distance 10 centimeters. Hope this helped. Thanks for watching.